This next video is on polyatomic ions. Now, polyatomic, poly means many, atomic is referring to atoms, so this is saying we have many atoms. A technical definition is when two or more atoms are covalently bonded together and behave like a single unit. Now, covalently bonded together means that there are going to be a lot of nonmetals that are stuck together and we're not going to break them apart. That clump of nonmetals will have some type of charge, either a positive charge or a negative charge. And because of that charge, they're going to behave like an ion, which is why we're including them in ionic naming. Now, you know your compound has a polyatomic in it when you see three or more capital letters in our formula. So for example, here's just a couple examples of different formulas. I'll just pick some of the main ones. NaSO4, we've got an Na, an S, and a 4. Those are all capital letters. We've got three or more. So somewhere in there, there's a polyatomic in here. I wanted to look at this one over here. We have a capital H, a capital C, a capital N. Somewhere in there, there's going to be a polyatomic. Down here, we can have them in parentheses. We'll talk about the parentheses later in this video. But if it's in parentheses, then it's already clumped together as a polyatomic. So the NH4 is going to be our polyatomic, and then the sulfur on the outside. We can also have a polyatomic that is bonded to another polyatomic. So you might have a very large amount of capital letters in your compound. So for example, the nitrogen, the hydrogen, the phosphorus, and the oxygen are all different elements from two different polyatomics. Now, for a detailed list of common polyatomics, you can check out the top part of your periodic table. I've kind of I've done the squigglies around them here, a little cloud. This is kind of hard to see. I'll rewrite for the purpose of this video. I'll rewrite some of the main ones that we'll see, but this is a detailed list. There are a lot more than just in this list. These are the common ones we'll see in general chemistry. For the ones that I want you to focus on for this video and the main ones for everyday use that we'll have, these ones here are going to be the main common ones. So NH4 with a positive 1 charge is ammonium. NO3 with a negative 1 charge is nitrate. SO4 with a negative 2 charge is sulfate. Capital O, capital H with a negative 1 charge is hydroxide. PO4 will carry a negative 3 charge. We call it phosphate. CO3 with a negative 2 charge. We call it carbonate. And then C2H3O2, that whole thing carries a negative 1 charge, and it's called acetate. So these are the common ones I'll be using in this set of videos. Now, if I'm writing the name, so if I give you the formula and you have to come up with the name, there's a variety of ways that we can organize our polyatomics. First, we can have a metal, and we can have a polyatomic instead of the standard nonmetal. If that's the case, then we're just going to put the metal name, and then we're going to put the polyatomic name. Now, something to keep in mind is that we've already talked about two different types of metals we can have. We can have a metal with a fixed charge, or we can have a metal with a variable charge. And if it has the variable charge, remember that we will need our Roman numerals. So the previous rules that we've already talked about still apply when we add polyatomics to our compound. We can list a polyatomic first. It could take the place of the positive charged substance. And then we can have a nonmetal. In that case, we're going to list our polyatomic first, and just like before, our nonmetal will end in an IDE ending. We could also have multiple polyatomics, two that are shoved together to make one compound. In that case, we'd have our first polyatomic and then our second polyatomic. Keep in mind that these are all ionic substances that we're naming, so we have something with a positive charge bonding with something else with a negative charge. So let's see some examples of these three different types. I do want to say one last quick thing. The rules that we've already talked about aren't changing. We still have to figure if it's a fixed metal, we still look on the periodic table and go from there. If it's variable, we're still using Roman numerals. That didn't change. If we have a non-metal, it's still IDE ending. The only thing that's changing is when we have a polyatomic, we're just going to use the name of the polyatomic instead. So all of our previous rules still apply. Okay, so a couple examples. First, Na2SO4. Well, Na is familiar with sodium. It does not show up in any of my polyatomics. Instead, if I look on my list, the SO4 is going to be what's clumped together to be my polyatomic. So, because sodium has a fixed charge, I can just put the name of this, sodium, and then my SO4 is called sulfate. That would be how I would name this. FeCO3. Well, if I look on my list, the CO3 is what my polyatomic is. So this is going to be my chunk of polyatomic. So I've got Fe, which is iron, and I have CO3, which is carbonate, but I'm not done yet. That's because iron is one of the elements that can have a variable charge. It can either be a 2+ or a 3+. So because of that, I need to have a Roman numeral that tells me the charge of iron, and I'm going to put it in parentheses. To figure out what that charge is, I have to look at what it's bonded to. So I have to go back. It's being bonded to carbonate. So let's look at carbonate again. It has a 2- charge. So carbonate, 2- charge. I only have one carbonate because this whole thing acts together. There's only one of those. So if carbonate's a 2- charge, I only have one iron to balance that 2- charge. So iron has to be a 2+ charge. So I'm going to put Roman numeral 2. Let's try another one with a variable charge because those are generally harder. Cu3PO4. Well, look on my list, PO4 with a 3- charge. That's what shows up to be my polyatomic, and we call it phosphate. So this whole thing right here is my polyatomic. We said it has a 3- charge, and so I don't keep flipping around my pages, I'm going to put phosphate over here. Cu is copper, and copper is one of those elements that have a variable charge. So we need parentheses around a Roman numeral to tell us that charge. Now, copper 3, PO4. PO4 has a charge of 3-. Notice that this 3 is also down here. We crisscrossed it, or backwards crisscrossed it. If you would like more notes on the backwards crisscrossing, check out my other 2 previous videos. To get the charge of copper, I can backwards crisscross the number of PO4s I have. Now, some people try to take this 4 and crisscross it up. That's not the case, though. This 4 means we have 4 oxygens that are glued together to my phosphorus. And by glued, I mean covalently bonded. So I can't separate the 4, and that's not the number of phosphorus or phosphates I have. Instead, I have to look outside of my outside of my 4. Well, I don't have any other subscripts. So I'm going to assume that I just have one PO4, which means that if I crisscross my 1, then my charge on copper becomes a 1. So copper 1 phosphate. These are all examples for when we have a metal followed by a polyatomic. Let's look at the next example. A polyatomic to start, and then a nonmetal with an IDE ending. Now, in order to start with a polyatomic, it has to have a positive charge. For general chemistry, we will only talk about one polyatomic that has a positive charge. It's NH4. Positive 1 charge, we call it ammonium. If your substance starts with NH4, we automatically know that that is our positive polyatomic. So, notice, for all of these next examples, They all start with NH4 because for general chemistry, there's nothing else to start it with. So let's name this first one. NH4 we said was ammonium. It has a fixed charge, it's not going to change, so I can just put ammonium. Sulfur would become sulfide. Again, I've got ammonium. The Cl is chlorine, which would become chloride. NH4OH. Okay, now we've got NH4 to be a polyatomic, but then I have a capital letter and another capital letter. I've got a lot of capital letters. Turns out that this is another one of my polyatomics. The capital O, capital H, it's my hydroxide. So we're now moving into this third part. If I have multiple polyatomics, 2 polyatomics exactly, then I just use each of their names. So NH4 we already figured out was ammonium. OH is hydroxide. And down here, NH4, ammonium. And CO3 is another polyatomic. CO3 is carbonate. So this is ammonium carbonate. I hope that was helpful for if I give you the formulas, can you come up with the name? Now, we're going to keep moving. So, if you are writing the formula, there's a couple steps we need to follow. So if I give you the name and you have to write the formula, we need to identify what the polyatomic is. And from there, we can get our charge. And that charge is shown on the list that we can look up our polyatomics. Then we determine the charge of what it's bonded to, and we just crisscross them like we have in all of our other ionic substances. Now, if you need more than one polyatomic in order to balance that charge, then we have to put a parentheses around the polyatomic, and then we can add the subscript outside of our parentheses. It kind of looks something like these, where we have them in parentheses and then we have a subscript on the outside. That's telling us that I have 2 of my NH4 in order to balance my CO3. So let's see a couple examples. Calcium carbonate, well, calcium is Ca. Carbonate is one of my polyatomics, CO3. Now, I know that it's a polyatomic and not just carbon because it ends in ATE. If it had an IDE ending and said carbide, then it wouldn't be a polyatomic. It would instead be just carbon. So I can look at the ending to make sure I have my polyatomics. Now, notice hydroxide ends in IDE. Well, true, but I don't have any element that's named hydrox. So I know it's going to be some type of polyatomic because if you looked for hydrox something or other on the periodic table, you wouldn't find it unless you look on your polyatomic list. Little side tangent. Okay, calcium carbonate. Let's make sure our charge is balanced. So calcium is a +2. I get that from the periodic table. Carbonate, I can get that from my list, is a -2. Now, because that's a +2 and a -2, these automatically balance. So it'd be CaCO3. I don't have to do anything else. Magnesium hydroxide. Magnesium is Mg. Hydroxide is one of my polyatomics, which is OH. Now, if I look at my charges, magnesium on the periodic table has a charge of +2. And hydroxide, being a polyatomic, has a charge of -1. I'm going to put a -1. Now, these are not equal, so I would have to crisscross my charges. So the 1 comes down here, the 2 would come over here. However, I don't need just 2 hydrogens. I want 2 of this entire polyatomic. I want 2 hydroxides. So I have to put hydroxide in parentheses with the 2 outside. Let me clean that up a little bit. It would look MgOH2. Sodium sulfate, well, sodium is Na with a +1 charge. Sulfate from my list is given as an SO4. And if I check sulfate, SO4 has a 2- charge. In order to balance these, I need to crisscross. So the 2 comes down here. The 1 could crisscross, or it's implied. So Na2SO4. Potassium nitrate. Well, potassium's a K plus 1. Nitrate is my NO3 with a -1 charge. +1, -1, they're already balanced. Copper 2 nitrate. Okay, now we have some variable charges. The Roman numeral tells us the charges. So copper is Cu. The Roman numeral says it's a 2+. Nitrate, it's the same nitrate from up here, so it's an NO3. And we have a -1 charge. So I have a +2 charge coming from my copper. My nitrate, my NO3, should cancel out that +2 charge. Well, right now, this clump only has a -1 charge. So in order to cancel that out, I need 2 of this clump, which is my NO3s, to get a 2 negative charge to cancel my 2 positive charge. Well, in order to have 2 of these, if I crisscross my charges, put it down here, right now, that says Cu NO3 2, but really it says oxygen 32, if you're not careful. So to make sure that we avoid that, I'm going to stick my polyatomic in parentheses. I'm going to clump it together, make sure that I don't lose any of my particles, and then I can double the entire thing. Let me pretty that up a little bit. Cu NO3 parentheses 2. A couple more examples like that. Iron, Fe, the Roman numeral 3 tells me I have a +3 charge. Hydroxide, we've seen it before, is my OH with a -1 charge. I need to crisscross these charges. Well, the 1 comes down, so I'd still have an iron. Now, this 3 would come over here, but I'm not just tripling the H, I'm tripling the whole thing, the whole polyatomic, so I stick it in parentheses. So this is FeOH3. And then ammonium oxide, well, we've already seen ammonium, we saw a lot of it, to be our NH4, with a +1 charge. Oxide is referring to oxygen, which has a 2- charge. If I crisscross my charges, the 2 would come down here, the 1 would come over here. Well, I can't have 42 hydrogens, so I have to stick that in parentheses so that I'm doubling the whole polyatomic, so that together I have a total positive charge. Again, the subscript multiplies to the charge, total positive of 2 charge, and then cancels out my -2 charge. Looks like I have 2 more examples, and then we'll wrap up. So cobalt, CO, 2+ charge. Phosphate is PO4 with a 3- charge. Crisscross my charges, the 3 comes down here. The 2 means I have 2 phosphates, but I have to put parentheses around it. So it'd be CO3, parenthesis PO4, end parenthesis, 2 on the outside. Ammonium carbonate, so this is multiple of my polyatomics. Ammonium, NH4 with a +1 charge. Carbonate, according to that list, is CO3 with a 2- charge. If I want these to balance, I need to have 2 of my NH4s. In order to do that, I have to put it in parentheses. I hope that was helpful for polyatomics, and good luck.